So how is it that, like, for the past 2 weeks so far, you've only been able to go on there? Now you have two windows combined.
Yeah.
But not that.
Well, that's a good question.
Is that TV on?
No.
I wonder, do you have to manually power it, or is it a... Maybe it's like this thing where the switch has to be on, because when we walked in, that TV was on. Like, you could tell it was the power was on to it.
Yeah.
So I don't know. All displays.
So the cubes is a mixture of Linux and Windows. You have the option to choose the Fedora, Debian, or Windows.
Oh, so it must be
You can run stuff on all.
it must be an overlay operating system that that's kind of sounds potentially interesting, actually. All right, so for today we explored this idea of asynchronous versus synchronous computing, specifically how it's kind of modified the way we solve problems. And I had a couple of questions about it. Actually, was some were interesting questions about whether are we talking in real life, are we talking for computers, a little bit of both. So, I mean, I think computers make the most sense if we roll back the clock, let's say 30 years. I mean, you know, it used to be I would say, well, you roll back the clock 10 years. Well, 10 years ago, computers were already really fast and doing stuff, so that doesn't really cut it anymore. But yeah, let's roll back the clock 30 years. The level of automation that we had through computing wasn't what we have today, right? So when I say that we historically have solved problems synchronously, what do I mean? What does that mean to say that we solve problems synchronously?
Are we sticking to the context of computers?
I don't necessarily care. I mean, I guess my preference would be yes, but that doesn't mean that something really interesting couldn't come out of talking about it outside of computers. So I guess just answer the question whatever way makes sense to you. What does synchronous problem solving mean, or a synchronous solution to a problem? Okay. All right. Do one thing at a time, or have whatever you're doing now prevents the next thing. So if we're kind of putting this in terms of computing, we might say it's blocking communication or blocking problem solving. If I'm ordering at McDonald's synchronously, that means whoever else behind me wants to order can't order until I'm done.
And nobody in any of the other lines?
Well, the other lines wouldn't exist. Yeah, in a synchronous problem solving community, the other lines at McDonald's wouldn't exist. It's a first come, first serve single line. Would that be bad?
Yeah.
So let's stick with the McDonald's example. At what point do you think they added the second register?
People were waiting a long time for fast food.
When people walked in, saw the line, and left.
Okay. So then you add a second queue to take orders for still one resource. Right? There was probably a transition period where they didn't put more cooks on the grill or something like that, right? So the idea was, we just keep the food coming. You know, I think at lunchtime at McDonald's, I've never worked at a McDonald's, but I assume at lunchtime they try to preemptively predict how many cheeseburgers and stuff they're going to sell, so they probably get a whole bunch of stuff cooking ahead of. We used to work at Little Caesars. I have to assume, like at lunchtime, you guys would kind of ramp up, so you had more stuff ready, right?
Right.
And then you got better at predicting how much more stuff do you have to be ready to handle the rush. All right, so we would add that second line. So if we just go to that second line, now we're taking a previously synchronous problem and turning it into an asynchronous problem. Now, what is the drawback of having that second line at McDonald's? What makes that more complex? So 10 of us walk into McDonald's, 5 of us go to one line, 5 of us go to the other. We're all putting in our orders at the same time. Well, whoever's got the register at the time is putting in their order. We have the one cook in the back. What's the drawback?
There's only one cook in the back.
Okay, possibly we're over.
We make so much food.
Okay, well, possibly we end up overloading the cook. But the hope is that with the cook going constantly and with 2 lines only, they probably can keep up. So the cook's the CPU, right? And they're basically processing any order that comes in. It comes up on the screen. They just keep cooking stuff, and they put what they were supposed to cook out, and then the cashier people bag it and decide, what goes where and that kind of stuff. Okay, so if we assume we're not going to overwhelm the CPU resource, so I think one thing we want to preface with this is if we think about computing today, whether it's network computing, scientific computing, really anything with computers, more than likely the last thing we're going to overload today is the CPU. The CPUs are pretty fast today. That doesn't mean you can't burden them, but their bottlenecks will be in other places before the CPU, at least more than likely. Okay, so we're going to say our CPU can keep up. So you have these two lines now. So what's the downside? What things can pop up having your McDonald's order happen asynchronously?
You could be getting two sets of different instructions at the same time from two different separate locations, and having to keep track of where those are coming from, what needs to be responding to which, that kind of thing.
Okay. Well, let's think about it in terms of human fairness. So I placed my order, and let's say you were third in line in the other line. And I'm first in line on the opposite line. So I've placed my order, and I'm waiting for my food. And person in front of you gets their order placed, and it's your turn. And all three of those people have food already. You've walked out with food. Your order was processed more quickly than mine. Why would that be?
You're bigger than they are.
It's a bigger order. We've never had anybody order the 600-piece nuggets. He said he got a coupon.
It's like In-N-Out, how they have you can basically choose how many patties and cheese.
Yeah, right.
I guess at one point somebody ordered 100 by 100. They had to limit it to 20 by 20 for max.
Like, sir, we don't have wrappers for that. Or, sir, that won't fit through the drive-through window.
Sir, it's not structurally stable.
There's a place like that in back in my competitive eating days. There's a place like that in St. Louis called Pointer's Pizza, and they had a pizza called the Pointersaurus, and it's the largest delivered pizza in the world. So the pizza, they had to make it so that the box would fit through the door, and they had like an extra wide door. So I don't remember what the weight of the pizza is. I want to say it's maybe like a 17 pound pizza or something like that. And they have a contest where if two people go in and can eat it in under an hour, you get I think $500 or something like that, and the pizza for free. And
Isn't that like Man vs. Food or something?
I don't know if they did Pointer's Pizza though. In fact, I'm not even positive it's still open.
This is in Chicago, right?
No, it's St. Louis is the pizza place. Well, me and one of my students from when I was teaching at Western Illinois University, we went down and did it.
You did it?
Well,
Did you succeed?
I ate my half and about a third of his half.
But did you succeed?
No, he failed me. We've been training in class, like we show up to class and we chug gallons of water. If I had gone in with the mindset that I was going to have to eat the whole thing myself, I think I could have. But I ran out of time. Like, I could have kept eating, but we didn't have
You
time.
never were a speedy.
Well, right, by an hour. I can eat 17 pounds. Well, that's a lot of pizza. But in the day, that's approaching call the ambulance, but it's, it was in the realm of possible. The problem is that much bread dries you out. Then you got to drink water, so it's not 17 pounds. Now it's 22 pounds of pizza and water.
Instead of, ribs, which is...
Oh, yeah. Prime rib. I love prime rib. Just awesome. All right, so minus my 600 piece nugget order, what are some reasons why orders would come out quicker? Type of food, right? Doesn't even have to be the amount. Maybe I ordered the fried chicken sandwiches, so it's going to take time to actually drop it in the fryer and cook it and stuff like that, where maybe the people in front of you ordered the cheeseburgers that were just ready to go.
Plain hamburger.
Yeah, whatever. Something that was just ready to go. Or I ordered a bunch of like special stuff.
Yeah.
It's like, I want this, no pickles, extra ketchup. A whole bunch of stuff where they had to like do the order extra carefully or something like that. I wasn't part of the conveyor belt of food coming out. All right, so from a human being's perspective, is that fair? We've adapted, right? So in real life, if you go into a place, as long as you feel like you're relatively being treated fairly, you're pretty okay with it. At some point, though, you complain. Like if you're at a sit-down restaurant and people come in after you and they have already had their food, ate, and left, and your food hasn't been delivered yet, then you start wondering, is something going on? Do they forget our order? That kind of stuff, right? So we do have our limits, but there's a level of acceptance. If we place our order and somebody else comes in 5 minutes later and they place their order and they get their food a little bit before us, we're not like complaining to the manager that we, who screwed this up? It was first come, first serve. That's within the realm of acceptable for human beings. Now that would be more of a server type of example, because now we are multiple human beings experiencing service from the same computer, right? If we're doing the sit-down restaurant type of example. Human beings tend to be more lenient when it comes to that. We understand that different amounts of food or different kinds of food take different amounts of time to cook and that kind of stuff. So as long as we feel like we haven't been left out, we haven't been forgotten, we typically are okay with it. And server class computing is kind of like that, right? You're not necessarily looking for real-time computing because you have this you have the concept that you are sharing that resource with other people. You want to feel like you can be productive in whatever you're doing. So one thing we might say is that synchronous versus asynchronous computing expectations change depending on whether we're on an individual, a consumer class computer where we're the only audience, versus we're on a server. So that's looking at it from the perspective of end user expectations. Now, if we're only looking at it from the perspective of kind of the problem solving process, how do we solve problems synchronously versus asynchronously, and what are the things that we have to deal with? And that's kind of what I was trying to get with the McDonald's example here, is when McDonald's has to come up with their plan for the lunch rush. And they're going to have 2 registers open, but they're going to have one person on the grill. What are some things that McDonald's is going to have to consider to make sure that they can keep up with demand as they're trying to solve a first come, first serve historic problem synchronously or asynchronously? What are some problems they're going to have to consider? We just discussed kind of human fairness, right? You can't have 30 people get their food before somebody who actually ordered before them. Could go out of order a little bit, but there needs to be a cadence where both lines are kind of getting served back and forth close enough, right? So we have to have some level of balancing that. We also have to have some level in the back of how the orders come into the cook. If you have, because now you have multiple variables there, right? You have 2 different. So, how many of you have ever been to a fast food place and you were in the line with the a person who was less skilled on the register, as opposed to the register next? The person next to the other register, they're just putting orders through like it's nothing. They're like an order-taking Jedi. Okay? You're in the line where this person is like having to call the manager over to void out French fries and stuff. So you're in the slow line. That now creates a cadence where you have one line, orders get backed up on the kitchen on one side, and even though you were physically there earlier, your order didn't get put in anywhere near the same time as other people, so you're going to be waiting longer. So McDonald's is going to have to come up with some sort of system for managing order load or something like that, right? To try to give some sort of semblance of fairness across the board. But things that they have to be concerned about is making sure that they fulfill every order, right? Because now you have orders coming in relative real time, because we're going to have 2 registers that are taking a cheeseburger order at the same time, and depending on how that order goes into their order queue, you don't want to have a situation where 1 cheeseburger for lunch and 1 cheeseburger for lunch turns into 1 cheeseburger for lunch instead of 2 cheeseburgers for lunch. Make sense? So some things you need to consider, that's going to be at their software level, right? As opposed to if we take the software out, we go back old school McDonald's. So, what did McDonald's look like in the what, 30s, 40s? When did McDonald's come out? Is it 50s?
You think we know that?
Well, I would think so.
How old am I?
Well, no, is it like a throwback thing?
No,
I think it's 60s.
60? It was before 60s.
probably 50s.
Yeah. I guess there's a really difference between 50s and 60s, but for some reason I'm thinking it's like 1930s. But regardless, before 55? Okay, before we had computers for ringing the stuff up, right? So for that order to go from the register to the person in the back, in the early days might have been a yell. Okay, I need 2 cheeseburgers. And you have everybody yelling over each other and that kind of stuff, and you're hoping the orders get in and things don't get lost and things don't get duplicated. You don't want to make 4 cheeseburgers if somebody only ordered 3, because that's losing money for the company and that kind of stuff. So can we all agree that there's an additional level of bookkeeping involved in solving problems asynchronously? Synchronous is easy, right? First come, first serve, one after another. We're not going to take your order till this guy's order's been fulfilled, till it's done. He's out of there. It's easy. It's slower, but it's easy. Soon as you make it asynchronous, whether we're talking about asynchronous in this situation, we talk about multi-core processors or multi-CPU machines or multi-CPU, multi-core machines. And we'll talk about kind of all these things as we're making some of these comparisons. Whether we're talking about, regardless of what kind of area we're talking about, as soon as we try to make things faster through asynchronous, we typically are going to increase our overhead. So, and that's going to take time. So that means that we use our example of a dual core processor. 2 cores in our processor does not make that processor twice as fast. I mean, unless you can literally divide all your work between 2 of them, and the nature of your work is they don't conflict with each other. So you don't have to have any overhead to check to see if this thing that's about to get processed on the CPU is going to conflict with this thing that's going to get processed on the CPU. If we just know everything is an independent job and nothing ever conflicts, then maybe you can get pretty close to twice the performance. But generally speaking, having 2 processors means you're going to have, let's say, 1.7 times the performance. Make sense? Because now you're probably going to have a 15% overhead of trying to manage the scheduling of those jobs. Similarly, here at McDonald's, are we doubling our throughput when you have 2 lines open? No. If we say it's like a CPU, our throughput is 70% faster, something like that. Than it would be otherwise, because there's an overhead scheme, or maybe it's 85% faster, whatever. There is a level of overhead for having 2 registers take orders for 1 grill. Now, does it get worse if we add a 3rd register?
Unnecessarily resources wasted.
Well, but let's say the load dictated it. So let's say it's a really busy McDonald's. So
Still,
We-
each customer will not have the same time to process their food. Will not expect the same time to process.
okay. Well, I guess what I'm getting at is what I say, is it going to be faster for 3 or is the same for 3? The real answer is maybe, right? There's probably some sort of sweet spot in the middle where we say, well, the difference between 2, 3, or 4 is negligible, right? It's not that huge of a difference, because the speed at which orders are coming in aren't going to necessarily burden the grill, as long as we limit the number of things to some maximum size. And then you can also play around with having more grills, and that also stretches the stuff out. But the point is that we can't just keep adding more and more registers and expecting us to always get more performance. Eventually, the overhead outweighs the throughput gain. Does that make sense? So, did you guys read about that in the book yet? Okay. So, did I give you at least one of the math problems that dealt with that, didn't I? For the homework? Okay. So, in any case, eventually, more is not better, faster is not necessarily better. There becomes the law of diminishing returns, where it sounds great on paper, but I think Intel, there was a story, I think last year, I want to say, that Intel has like 128 core general purpose CPU they've built. I mean, it wouldn't fit on our traditional motherboard. I think they have it sitting on, like, it basically looks like a microwave or something. But, you know, they have effectively a Core i7 128 core. 128 core processor. Now, to any of us, it's going to be like, well, that sounds pretty legit. It's like, okay, what are you going to use that for? You know, on your best day, you're going to take advantage of 5 or 6 of the cores. Okay, that's best day. So you have 122 cores just sitting there doing nothing. Yeah, but I have them. You know, it's just like people who have, I think I probably referenced it last class or something. If you have a Ferrari, but you never take it on the interstate or something, driving around residential neighborhoods. Yeah, it's like, oh yeah, I've never had this thing over 35 miles an hour. You just need a bicycle for that.
Afraid the air friction will scratch.
So is the point where it doesn't make sense. All right, so let's kind of pull this back towards computing a little bit. So when we talk about some of the things we need to consider when we're problem solving asynchronously, when we have 2 things happening at the same time, from a computing problem solving perspective, what are some things that we need to be careful of? Because now we're taking it away from, like, I mean, in every case, my lunch order doesn't necessarily conflict with Tim's lunch order. It's not like, you know, my cheeseburger has to be done cooking before his French fries can be eaten. Right? We don't have that problem in the McDonald's scenario. It's just about human emotions and whether or not you're going to get ticked off because your food is going to take too long. But in this case, if we have asynchronous computing, whether it's downloading 2 files for doing networking stuff, or we're number crunching this and we're number crunching this, we have the issue that one of these guys might be reliant on the other. Make sense? Now, sometimes, if they're completely reliant on each other, that is, we cannot do this until this has been complete, are those jobs candidates for asynchronous computing? They're not. We cannot do it at the same time, right?
The tasks assigned to those machines are not mutually exclusive.
That's right. If the tasks are not mutually exclusive, you cannot do them at the same time.
Yep.
All right. Now, so sometimes you have that. So that makes the job relatively easy. It's like when you have a situation where this has to happen before I can even start this. Okay, well, those guys are synchronous. Okay, relative to each other, those are synchronously scheduled, whatever they are. Well, then you have probably the more common task, the more common thing that can happen asynchronously. We have 2 things that we want to happen at the same time, and we can't do the next thing over here until this guy is done. Okay, so if we give ourselves a real life example, let's say you have an app, and the app is launched, and maybe you're grabbing the user profile information, something like that. And let's say the screen the app takes you to is, you know, some sort of home screen that is mostly kind of generic interface data that's on there, and then maybe at the very top it has the user's current, maybe it's fantasy football, so it's like the user's current record or something like that. Okay, and that would be a piece of information that would be reliant on this data. Hello.
Just a drill.
Oh,
Yeah, it should be done as soon as we get the kids out of the dorms.
okay. Do we pause this? Or is this just pause? Okay. So when we're
Now that half the classroom is burned down.
the rubble. Has anybody seen my shoe? Okay.
Wait, gotta find my MacBook.
So when we're doing things asynchronous, so I gave a scenario where we have an app and there's a large portion of the main screen is static data, can be loaded at any time, but there's a couple of pieces that are specific to whatever user just logged in. Maybe it's just their username or their fantasy football record, something like that. Well, we have a couple of choices. The synchronous approach to this would be to do what? It would be that I'm not going to even show that screen. I'm going to pause the loading of the app while I finish retrieving your profile information with your team's record. And only once I have that data and can insert it here will I show you the screen. That would be the old way of doing it, right? That would be a synchronous approach. I can't show you this screen until I have everything that needs to go on that screen available to me. As opposed to an asynchronous approach where I can show you 90% of the screen right now. It is not reliant on anything else. Boom, here's your screen. Now, while that guy's up on the screen and the human already sees it, and the human might be already clicking and scrolling on stuff, I'm still downloading their profile information over here. And as soon as I have that record, I'll update the screen with that data. So it shows up as soon as I have it. So now what you've done is you haven't slowed down the user experience. The app is clicky, doesn't feel locked up or paused, and just some data is not available yet, right? That feels more like the modern way of doing things, doesn't it? Is that always better? Okay, so really it probably comes down to our go-to answer of it depends, right? And a lot of this is about end user expectations. So with end user expectations, as a general rule, users don't like to wonder whether the app has crashed, right? So there are probably situations where it would be appropriate to give them a little loading thing that's spinning so they see, oh, it's still alive, it's loading. Maybe even a percentage that shows you kind of how far loaded it is, so you know if as long as it's ticking up, we're okay. Right, exactly. As opposed to taking them to a screen that doesn't have all the data on it yet, or at the very least, sometimes you'll have like the little load circle things at those the hot spots on the screen where stuff is still popping in, but you can still navigate through the app and things like that. So I think we have, as in general, as a user, especially as our smartphones keep getting faster and faster and faster, we have this expectation that our devices will do whatever we want them to do as soon as we're ready for them to do it. All right, so typically asynchronous is going to be preferred by the user just so it feels like our devices are clicky or fast. But now, asynchronous communication creates a new problem. So just as we just decided that a majority of the time asynchronous communication makes the most sense, to the point that there are many APIs, programming APIs, that only do things asynchronously today. So let's take an example where I really need this data before I can do this thing. But the nature of the networking API I'm using to grab that data off the internet, it's a non-blocking API call. It's not going to keep me from getting to this line of code. It doesn't sit here and wait till the data is available and then get to that line of code. I make the request, it's an asynchronous request, and we immediately hit this line before we have the data. So now we're in a situation. I have a screen, so we gave the example before, where a majority of the screen is something that is not reliant on data, that the fantasy football score. Let's say we have a screen where 100% of the screen is reliant on data being available. 100% of it. Nothing on that screen is worthwhile putting on the screen unless you already have the data back. Make sense? How do we solve that problem? I have a tool here. Okay, so we have this cool networking API thing that says we're the latest, greatest, coolest, and we can only do things asynchronously. That's it.
So Firebase.
Well, Firebase is actually is a good example. Firebase is asynchronous. I mean, all of the modern ones are asynchronous only. Alamo Fire for iOS development is asynchronous only. Pretty much all of our network connectivity stuff is asynchronous today. And most of the time that's fine. You know, that example of being able to use a screen and then having a little thing pop in when it's ready, that's great, right? That's where asynchronous thrives. That's a great example. But now our tools have decided they're always asynchronous. They don't have a synchronous mode. In the transition years, when asynchronous was kind of popular, but there was kind of a time and place for both, you would have the option. Do I want to make this call synchronously, or do I want to make this call asynchronously? If you've used parse.com before, parse gives you the option. So you can get something in the background with a callback block. So you pass it a function that says, okay, once I have it, I'll call this function. And then in that function, you do the stuff that you would do when the data is available. Update this label or something like that. Or that would be to do it in the background asynchronously. Or you can do it synchronously. Get this data. Do not continue on until this is complete.
Does parse fully shut down?
It should be.
Well, no, it's their servers officially go down on January 28th, 2017. Huh?
I thought they already went down.
No, they basically said we're shutting down. It'll be exactly.
But parse server you can run on your own.
Yeah.
So I have a couple of projects that I've migrated off of Parse's thing and have it running on parse server running on Heroku or something. And so it's still there. If you like parse and you want to do things the parse way, you can do it the parse way for.
Yeah.
For
You
a
can't
long time.
use their service.
Correct. Well, for right now you can.
Yeah.
But
Not for long.
yeah, not for long. Correct. So in any case, our go-to tools today, any new tool that comes out. So parse is a little bit older, and it's fallen to the wayside, I guess. Any new tool that comes out is most of the time asynchronous only. We don't have an option as a programmer. And that hurts us. That's a constraint that's put on our problem solving from a programmer's perspective, right? We have to decide, okay, the easiest way to do this would be to do this synchronously. Because I can't have this happen until this is done. But the tool that I have, when I request this, I cannot do it in a blocking fashion, in a synchronous fashion. As soon as I make this request, boom, I'm on that next line. And I'm doing stuff with data that I don't potentially have, that I probably don't have. I don't care how fast your internet connection is, and this kind of goes down to throughput, which is likely going to be faster. The amount of time it takes to retrieve data over the internet, over the fastest internet connection, or the time it takes to get to the next instruction locally on the CPU. Time it takes to get to the next instruction locally on the CPU will be faster, even on slow CPUs. Because part of that networking stuff was instructions on the CPU to make that call. All right, so you're always going to lose that race, is the punchline. So if this guy doesn't block and you need the data here, you will never have the data there. That's a problem. So how do we solve for that?
Infinite loops.
Just busy wait loops. That I don't think I told it in here, but I've told the Double Dragon story before, right? In some of my other classes. I had there was a game that was popular in the arcades when I was younger called Double Dragon, when arcades were
You told us
existed.
this last class.
Okay, yeah, that's why. So you start relying on busy wait stuff as computers get faster. That waiting wasn't quite enough. But it actually is an interesting thing you brought up. I mean, I know it was meant to be funny, but it's true. I mean, that is a potential solution. I think it's going to take about this long to get that data.
It's a roundabout way.
Okay, we're crossing our fingers. It's like, okay, worst case scenario, two things are going to happen. I mean, if you don't have the data by this point in time, the app's going to crash anyways. So we're going to give them a busy wait loop that just sits there and burns time
Or in some cases.
for
burns
5
the
seconds. At the end of 5 seconds, we're either going to have our data or we won't.
phone. Or just.
And in any case, I'm going to show the next screen that is relying on that data. And if the data's not there, bad things will happen.
Or if it's a Samsung, the phone may start on fire.
Can you believe that? Man, Apple has to be so happy right now.
Well, when it gets to the point where airlines say, "Please do not bring this phone on our plane,"
I mean, as if Apple wasn't already selling too many iPhones, right? I mean, I'm an iPhone user, but I'm a huge advocate of competition because it helps everybody.
The past 2 days, they've gone up 2% each day.
Apple has?
Yeah.
Okay. But just in sales, though, I mean,
Yeah.
as a technologist, I want great technology.
Mhm.
I frankly don't care who makes it.
I heard that they like increased their requests for parts.
Yeah,
Who, Apple?
yeah. I mean, they already sold more iPhone 7s than they sold iPhone 6s, the 6Ss. But now they're going to sell like way more because Samsung, people don't trust. I mean, no parent's going to buy their kid a phone from the company that phone blows up in your head. So it's going to be interesting. Hopefully, it doesn't hurt. I hope it's a very temporary thing for Samsung because in the smartphone industry, we need Samsung. And you need those 2 or 3 big players to produce the. I mean, there's a zillion Android phones, but there's only a small number of Android phones that are on even keel competition with Apple's products, right? You know, you have the low budget pleaser smartphones.
Who would you say is right behind Samsung?
Oh, HTC, LG. I mean, companies that you've heard of, that have money behind them.
I've heard BlackBerry, but that doesn't have anything to do with.
Well, you know what I mean. Yeah. So, I mean, we need the companies that are they're willing to have the premium line phone. You know, because when people talk about Apple, it's usually, oh, their stuff is too expensive. There are plenty of other smartphones that cost just as much as the iPhone. But the majority of Android phones cost much less, but they're also not the same
Just
level
imagine
of.
like the hardcore Samsung. Well, I don't have fingers, but I'm not buying an Apple.
Not buying an Apple. See, this right here, this is a skin graft from an elephant. This whole thing's a bear claw.
I don't have fingerprints. Maybe I can join Men in Black as a fallback.
All right, so one possible solution to the asynchronous problem could be that we come up with random busy waits and just hope it's enough time. And you know what? This is actually, we say it kind of jokingly, but it's pretty important because these are hard bugs sometimes to find in software. And what I mean by that is sometimes you'll have something that works on the simulator or on a faster smartphone, but on a little bit slower one, it doesn't work. All because you didn't do something correctly, but it just so happens that this guy over here always barely wins the race. He barely has the data right before he gets to that screen. 99% of the time. Where this guy over here has it 20% of the time. And now you have the same software running on 2 different phones, and it might just be the same. It might be the iPhone 6 versus the iPhone 6S. And it crashes all the time on one of them and never crashes on the other. What do you to suspect? You don't think it's the software initially, right? Oh, it must be your phone. It must be something else. So this becomes a fairly hard problem to deal with. So what we want to think about is the problem-solving approach to dealing with this appropriately. So the correct answer is not to put in a busy wait loop or to put the thread to sleep. Like, just sleep for 10 seconds. I'm sure we'll have it by then. We'll just see what happens.
The internet's down. Well,
So what's a solution?
Put in a placeholder.
Okay, so we can have placeholder data. I guess what I'm really getting at is how does this second screen, the screen that's reliant on that data, we're going to show them. It's not blocking, so that second screen is going to get thrown on the screen. So you're going to put a placeholder in. It's like, well, we don't want to be naked. Okay, so we're going to get that thing on the screen. So it's like, okay, I'm loading. Just don't complain yet, because this thing's still cooking. But how does this guy, the screen that's loading, waiting for its data, how does he become aware that the data is available?
listeners.
Possibly something like listeners. But let's take this to the real world. So let's say that come up with a reasonable example that can happen in real life. Okay, yeah, this would be a fun thing. So let's say we're going to do something potentially borderline with drones. Okay, so Tim is going to run over to one side of campus. Okay, and we're going to...
I'm walking.
All right. Well, you're gonna have some. It's gonna be a corn dog. All right. So I'm hungry, and we want to use. Maybe we have some sort of computer site thing we're going to use so that a drone takes off from this side of campus, flies over the buildings to the parking lot over there, picks up the corn dog from you, brings it back to me. Okay. Now you're going to have some sort of
fight the drone.
Yeah. You're going to have some sort of sensor on you that's going to be flashing if the drone uses to hone in on. Okay. So we throw the sci-fi stuff in there. Okay, we got that. Now, I can't let my drone take off until you're in place in the other parking lot. Make sense? All right, so now we have a bunch of buildings in the way. So it's not like I can stand over there and just watch till I see the green hair. You know, like, oh, I think it's still, he stopped moving now. We're good, go. Okay. So when you get into position, you have to notify me somehow. So what would be our modern human way of doing that? Yeah, you text me. Tim says, I'm here. KK, thanks. Right? And then I have the drone take off and all that stuff. So these are two completely separate processes. This is the getting the data over here. This is waiting for the data to be available. And as soon as this data is available, it communicates with this guy somehow. Now, how is he able to text me? What information do you need in order to be able to text me?
Your phone number.
My phone number. Okay, so presumably I had to provide him with that number. We had to agree that it was okay to text each other, right?
Is this some law? I don't know.
I mean, how many numbers do you think the right guy has that weren't given to him?
2.
All right, so yeah, so
Mom and Dad.
Mom and Dad. Okay. So in any case, you and I had to agree on this communication protocol. Okay, so you have the ability to send me a message, and I have the ability to hear a message from you. Okay, so I am a listener. I'm an observer. Okay, in some of the other classes we've talked about the observer design pattern. Okay, what's the deserter design pattern?
Run.
If there isn't one, we should have that. That's a research paper. Because I remember when I first taught design patterns in some of those other classes, we talked about they always have to have a funky name. So you got to have the deserter design pattern.
You don't get the data within 5 seconds, you just leave.
You just go. Okay, so we have the observer design pattern.
Wipes your phone.
What does the observer design pattern say? What's the premise of it?
You look at stuff.
Somebody who remembers from when I taught him. So he has an excuse. He didn't have the class with me.
Which class were you referencing?
I talk about design patterns in a lot of classes. So
It's a good idea to be doing something while you're waiting.
Yep. So effectively, asynchronous, right? It's almost like synonymous with the idea of asynchronous commuting. So we're saying, look, if you're waiting for something to happen, it's a good idea to do something productive while you're waiting for it to go down. Make sense? So while Tim is running to the other side of campus, walking, whatever, with his corn dogs, all right, which kind of sounds creepy to begin with, but anyways, you have a dude with green hair sprinting across campus carrying corn dogs. I don't know what you're supposed to think.
That'd be the time that I just mess with people so bad.
Did you see him? Did you know where he's at? Don't tell him I'm here. All right, so
See, that's why I'm running with the corn dogs. You sending the drone after me. The fat man wants my corn
what's
dogs.
the corn dogs? All right, so the idea here is that while I'm waiting with the drone over here for Tim to get into position, it's not that productive for me to sit there and just wait on the text message to finally come in. I should do something else productive. Maybe I check on my World of Warcraft bot. Or I check on my Hearthstone bot. I check on my Pokemon Go bot. Okay, so check on one of my bots, see the current situation, and then finally, I'm notified by Tim. I'm brought back to reality that he's finally in position, and now I can launch the drone and go do the attack, right? To get the corn dog. So this type of thing would be an implementation of the observer pattern. Let me know when you're ready. In the meantime, I'll go and do something else. So we would have to have a mechanism in place for receiving notifications. In our case here, it just so happens that the cell phone communication network has provided us a mechanism for sending and receiving notifications, right? Did I do something funny?
No, I'm just imagining like you sitting in front of like the chapel courtyard or something.
With a drone?
On your head, like somebody watches you, send this drone away, it comes back with corn dogs.
It's like, and I know that sounds weird enough as it is, but he's out there, he's wearing a tie and a Speedo. That's it. There's nothing else there's nothing else on. Okay. And the Speedo's a rumor.
I could just imagine like Gretchen yelling at you from the cafeteria.
You have to catch me first.
Blacklear's like walking out there with a stern face.
I don't know. I really don't know how to handle this.
Walt's probably taking pictures.
I was talking about that with a buddy the other day, because this would probably work. So let's say that you're, I'm not condoning this. None of you should do this.
Do we need to pause the recording?
No, I mean, it's more just kind of a funny thing that when you think about it, it's like, that probably would work. You shouldn't do it, but it probably would work. So let's say you're an older person, it's kind of time to get into an old age home. And this is a real common problem in the world today, is that folks who need to be in a place like that can't afford it. It's expensive. And then there's different levels. So the ones that can afford it get into nice places. The ones that can't get into places where it's questionable. And you have these issues where, well, do I really want to put, mom there? That type of thing. Well, couldn't an old person walk into a police station and say they committed a crime? Whether they did or not, it's got to be a bad crime. That way they lock you up. Okay, so
3 meals a day in jail.
Well, but it can be even better than that, because if they think you're crazy, don't they put you in like a nice place? Yeah. So look, I think I killed somebody. I don't even remember. I don't know my name. Is my name Sharon? That doesn't sound like a Sharon. You start having these conversations with yourself. They're feeding you.
Like a Sharon, stop it.
Yeah, they're feeding you. They're putting you in like a nice, loony bin. I mean, that would probably
They're
work.
gonna find some meds to give you.
Huh?
They're gonna find some meds to give you, and that might.
Well, yeah, and then you'll be crazy. Like, you'll like legitimately be crazy.
If there's anybody who can do it, I feel like you could pull it off better than those people. Just walk in. Don't stare at him like that.
Don't stare like.
Stare at you like anything. You just go up to him, look him in the eye. Do you know that blood tastes just like the pie my mother used to make?
But that would work. All of a sudden you're in this like plush place with padded walls. They're giving you, nice meals, nothing with sharp edges. So, I mean, sounds bad, but it would work.
You gotta keep it up though. You gotta keep up the crazy.
We already solved that. He said they're going to give them drugs that make them crazy.
Yeah, but a lot of times if you're not actually crazy, the drugs make you crazy.
That's the point.
Yeah.
He doesn't have to keep it up. He will become crazy. Because they're going to be treating him with stuff for things that he doesn't have. Now he's crazy. Now he has it. Now he belongs.
Problem solved.
Problem solved. It's like, yeah, it was a little unethical how I got here, but now I should be here.
Isn't that a thing though? Like homeless people in the north will commit crime times during the winter so they can do it.
Yeah, I think so. So I mean, it's
I got yelled at by a homeless guy the other day. That was fun. Like, just walked by him, didn't say a word, just turns around and starts screaming at me and like.
well. Did he
words
see your green hair?
Oh yeah, but I got like a myriad of reactions to that. It was the first time I had somebody scream at me in general. It was funny. Some old black dude just walks by and he went from like a mix of like screaming and grumbling. He's like, "Oh!" I just kept walking.
So he was drunk.
No, he's just crazy. See, what I usually do, my level of sobriety at the time usually will determine is I'll just, if they ask me for money, I just start speaking in German.
Why don't you just sit down there with him?
Because I want to go home.
Yeah, I think that would be a pretty entertaining, like self, camera thing, right? Do have the video going. He's yelling. He's like, "Oh, thanks." I'll pull up a chair. You sit down right with him and almost like lean your head on him, like you're taking a nap. See how that goes.
I know how you feel.
Yeah, man, she did the same thing to me.
No.
I would-
said that?
I would make such a great crazy person. I know. It'd be so easy.
I meant like.
All right, so let's finish. Let's finish this discussion so we can take a break. All right, so we have this idea where now we need to have some level of communication between the two parties, some notification system, and that's an implementation of the observer design pattern that allows two asynchronous things to get messages to each other, possibly messages with payload. That is that Tim might not just let me know that he's ready. He might let me know that he's ready as well as maybe his GPS coordinates or something like that in the event that my drone isn't able to like hone in on him or something like that. So he might need to also get me data.
It blended with the grass.
It's true. So we have mechanisms for that, and any software development infrastructure you're working in today is going to have a mechanism for the observer design pattern, and most have several to choose from to handle messages like that, because it's a new way of problem solving. It's a new thing we have to be concerned about. The things that it takes to make our applications feel like they didn't pause, they didn't hiccup, things like that, are also things that mean that we need to have some level of communication over and above what we used to have in order to make sure that we don't try to show data that we don't have, but we become aware that it's time to show the data when we do have it. Does that make sense? Okay, so it does change the problem-solving approach when we're moving from synchronous to asynchronous, and that's not dissimilar from multiprocessor computers in the earlier days of operating systems, where they had to create CPU schedulers for dual core. Well, in the early days it was dual CPU computers as opposed to a single CPU. And two CPUs isn't necessarily faster than one if you do a crappy job of scheduling or don't even try to schedule. That was Apple's, we mentioned that last time, Apple's thing. So, that was their thing. They said, hey, here's another processor. Our software doesn't try to use it. So paperweight is what it is. But it will cost you more money to run this computer because it's got to power an extra thing. Okay, so that's kind of our deal with asynchronous computing. So certainly a change in our problem-solving approach. I think we could probably all agree that for the most part it's for the better, but does put some new constraints on the way we solve problems. And when we take this down to the hardware level, if we're thinking about a CPU that has to handle things communicating isn't that the next logical step? We're doing this at the software level. Well, now we're talking about having, when we talked about what a CPU actually is, we said it's kind of a bunch of programs written in hardware, right? A bunch of little magic tricks written in hardware. Well, at some point, and we already have, but we're going to have some of those magic tricks that work in parallel, that do two things at the same time because they can. But now we're dealing with stuff at near the speed of light, of making sure that this guy doesn't complete the circuit before this guy's ready or something like that. All right, so this is going to be an ongoing problem. So our approach to solving the problems has changed. And so just kind of the last maybe short discussion related to this is how long have people been solving problems asynchronously? Is this new for people?
Long time.
Oh, a long time, right? It's natural for us. It's natural for us to try to be as productive as possible, isn't it? Why wasn't it natural for computers, for us to solve problems on computers in an asynchronous way? Well, we're the ones who programmed it. Okay.
We can think parallelly, but computers cannot think parallelly. We need to,
Well, but we're the programmers.
yeah, we need to make them to accept some other request while it was in the ideal state.
Right, but the computer's not doing anything we didn't tell it to do. Why weren't we telling our computers to work in parallel, to work asynchronously?
Didn't have the hardware to do it.
Okay, hardware limitations. So it could be speed, could be communication stuff, right? So let's go back to the early days of computing. I mean, we take for granted a lot of the things computers can do today, but I mean, like we assume the internet is we take that for granted now that two computers can communicate with each other. You know, but actually down here is a good example. So what we got? So who in here is on Android instead of iOS? All right, so we could not message each other right now because I have no service. And you probably have no service unless you're on Sprint and you have 11 bars.
I guess I'm on Sprint, but I have Republic Wireless, which just throws everything on the Wi-Fi. So
Okay,
I can do anything.
gotcha. Well, so on an iPhone, actually, would it work on here? Can I get a text message through the Wi-Fi? I might be able to with AT&T. Yeah, I think I can. I think I can with AT&T now. But so let's go back 2 years. Here, we're back 2 years. So because we wouldn't be able to take advantage of iMessage, Apple to Apple communication, you know, and because we're down in the basement here or whatever, we have no service. We're out of communication. So that breaks some of our options for communicating, right? Good thing we're 10 feet from each other, so we can pull it. I can project. But the reality is that in the early days of computing, having two computers talk to each other wasn't a thing. It didn't exist. We had limitations on the hardware. We had constraints. Human beings have been able to talk to each other forever, right? We've been screaming across the room, screaming across the field, whatever it is. You know, we like, are you ready? Yeah, I'm ready. Just throw the spear. All right, so we did have limitations with the hardware, so it had to catch up. But the one thing, I'll just leave you with this thought before we take a break, but something to kind of keep in mind, and you can use this as, I mean, I'm sure we can come up with examples that contradict this, but I feel pretty confident in saying that more times than not, significantly more times than not, the way we solve things in the computing world mimics the way we solve things in the human world. Right? So, and where I think it's easy for us to get into this, have this sense that computers are different. They're like aliens. You have to deal with them differently. They're us mimicking the way we already solve problems, but just in a really fast way that makes less mistakes. Doesn't get bored, doesn't get worn out, that kind of stuff. Make sense? All right, let's take 10. So 7:35, come back.